Hello. So we've been finding the continuous time Fourier transform of aperiodic signals now. And it sounds weird or feels weird, but we're going to go back now and figure out the Fourier transform of periodic signals. You see, our analysis so far is still incomplete. We have the frequency content of periodic signals is on one hand found by the Fourier series, and then the frequency content on the other hand of aperiodic signals is found with the Fourier transform. So we have Fourier series for periodic signals and we have Fourier transform for aperiodic signals. We want to unify the analysis, and so we need to figure out a way of getting a Fourier transform for periodic signals, and so that would thereby uniform the theory, and then we'd be good to go. So that's what we're going to do in this video. So remember, the Fourier transform, we've been using capital X, and Fourier transform is found with this integral. You give me x of t, and I'm going to perform this integration. That should be dt. This is the analysis equation, right? And so you give me x of t, and I perform this integration, I get the Fourier transform of x of t, which is capital X of j omega. And then remember, there is the synthesis equation where if you give me the frequency content, or the Fourier transform, capital X, then I will calculate this integral and get you back x of t. This is what's called the synthesis equation. Now, let's consider what, again, the capital X is telling us. And that is, it's telling us the frequency content of the signal, the frequency content. So, if I had a periodic signal, like, how about a basic signal like this? Right? If you remember, this was our basic building block, and this has exactly one frequency, omega 0. So for example, e to the j 2t has exactly one frequency, 2. And so if I looked at its frequency content, like if this was omega, and here's the origin, what would I expect its frequency content to look like? Well, why would I expect any energy other than at 2? So I would expect some sort of impulse, some sort of thinly, fine plot of energy right there at whatever frequency that is, and 0 everywhere else, because it has no frequency anywhere else other than omega 0, right? Hopefully you're with me there. And so we look at this integral, we say, I would expect, so if you give me a periodic signal x of t, remember this is periodic, definitely. If you give me a periodic signal x of t, then I would need to get an impulse out. So what possibly would I integrate here to get an impulse out? No such function where you integrate it and you get an impulse. So that's actually not going to work. And you could look at it another way. If x of t is periodic, that means it goes on forever and it cycles forever. And so when you integrate something that goes on forever, right? You're not going to be able to integrate it from minus infinity to infinity. If you're not going to be able to accumulate area that goes on for infinity time, right? And so what all that is to say, if you give me a periodic signal, this analysis equation will not converge. And that is technical speak for you won't get an answer. You cannot use this equation. So how are we going to do this then? Well, we're going to do it kind of by a reverse process. So let me suppose that I have a Fourier transform that is given by this. Okay, so that that's what we're talking about here. We've got an impulse, right, at omega 0. delayed by omega 0. So there it is, scaled by 2 pi. So let's suppose I have this transform, and I want to know what is its x of t, right? What is its x of t? Well, I'm going to use the synthesis equation. So that I can do. I can integrate an impulse. So let's do that. So if that's the case, notice the 2 pi's will cancel, and I'm left with the integral from minus infinity to infinity of delta omega minus omega 0 e to the j omega t d omega. And what is that integral equal to? $1,000,000 question. I'll pause the video if you want to think about it, but this is from the sifting property. So here it comes up again. Sifting property of the impulse. That is equal to e to the j omega 0 t. So there we have it, actually. So what we're saying is that e to the j omega 0 t, this basic building block sinusoidal signal, has Fourier transform 2 pi delta of omega minus omega 0. So we were right. We were right. This basic building block has one such frequency, and its Fourier transform is an impulse at omega 0, just like we expected. Okay, so that was one case, right? That was this one case. Let's see if we can start to generalize this now. So remember, we're talking about periodic signals. Well, any periodic signal has a Fourier series, right? And so let's, for now, so this is now we're going to try to generalize this new problem. So let's say now we have not just one impulse, but a bunch of impulses. Let's say we have a bunch of impulses, potentially infinity impulses added together, scaled by 2 pi and maybe some constant. Maybe the constant is different for each impulse. Okay, so what we're saying is that we have a sum of a bunch of impulses. So just a bunch of impulses that are equally spaced by omega 0, some constant omega 0, and that have their own scaling constant ak. So we just have a bunch of impulses. Suppose that's our transform. So let's just be concrete here. Let's just draw one possibility. So maybe I have an impulse here, and maybe I have another one here at some number, and then maybe equally spaced I have that one, and then maybe I have something here, and maybe I have something here, right? This would be a sum of equally spaced impulses, each scaled by their own scaling coefficient. Okay, so let's say I have something like this. We're going to keep it very general. What would the signal be? That's what we want to know. So let me use the synthesis equation. Okay, and I'll put in capital X. I can take the 2 pi out of that sum, actually, and so that will actually I'll just write it for now. I'll take the 2 pi out of the sum. K goes from minus infinity to infinity. AK delta of omega minus k omega 0 e to the j omega t d omega. So this is a straightforward application of the synthesis equation. All right, just plugging in x for x up there. Now the 2 pi's will cancel, and I can switch actually the order of the sum and the integral. Right, the integral of a sum of things is the sum of the integrals. Right, so I've got this. Right, now from the sifting property again, what makes this argument of the impulse 0? Well, when omega is equal to k omega 0. So that whole integral from the sifting property, check that property out if you are not up to speed on it, is that whole integral is equal to e to the jk omega 0 t. So that goes away, and so we're left with this. So we're saying this has the Fourier transform this, right? This is what we started with. So we kind of did this backwards. We're trying to find the Fourier transform of a periodic signal, so we just guessed the shape, and we found that its signal is this thing, right? Its signal is x of t here. Well, what is that? Well, that's the synthesis equation of a periodic signal with Fourier series coefficients ak, right? So this has Fourier transform, which is a sum of 2 pi times those Fourier series coefficients times shifted delta functions. So what does that mean? Well, I'm going to write it out, actually. That means the following. So first of all, let me just be concrete again here and say I'll just speak to you blatantly here. You cannot use the analysis equation to find the Fourier transform of a periodic signal. We said that equation or that integral does not converge. So what do you do? Well, how can you do it? Well, according to what we just found here in the box, for a periodic signal, you find, so I'll just say instead, find its Fourier series coefficients, okay, AK, right? We know how to do that. We did that many times. And then the Fourier transform is simply this thing. That's it. That's it. And you know, it makes sense. It makes sense that the Fourier transform would be related to the Fourier series. What we were saying all along about the Fourier series was that it tells us the frequency content of the periodic signal. Well, what we've been saying about the Fourier transform is that it tells you the frequency content of a signal. So those two things should be very similar. They should be related. And so we do find that the Fourier transform requires the Fourier series coefficients. So if that did not make sense to you, I've got some examples coming your way. I'll see you in those videos.